Hello everyone, and thanks for joining us for today's webinar from EDRMedeso. We're all super excited to get started, but first, a bit of housekeeping. Our technical team who are speaking today have worked hard to keep within their allotted times. There's just so much to talk about, so this presentation will more than likely run for the full hour, which does mean that we won't have time for the usual Q&A at the end. However, we still want your questions, and the ability to type them in and fire them over is still very much here. So please do ask away. We will respond to everything post-webinar. So, with that all said, I will now hand over to Stephen Sylvester.
Thank you. Hello, everybody. Welcome to this webinar today from EDRMedeso. We're going to be talking about space applications today. Space, the finite frontier. Obviously, finite referring to finite element methods and finite volume methods, which underpin all simulation technology. The content today has been prepared by myself, Stephen Sylvester, so I'm the UK Technical Director at EDRMedeso. My background is fluids physics, and my colleagues Fatima Hovidazavi for electronics and Richard Davies covering structures, respectively. So before we get into the technical aspects of the webinar, I'm just going to do a quick introduction to the company, EDRMedeso. I think there's probably many people on the call today who are perhaps not familiar with who we are. So a quick introduction. EDRMedeso was formed in 1986. We are an elite Ansys channel partner, around about 160 employees. It's really our goal to ensure that we get as much adoption of simulation software into the hands of engineers and designers, and to make sure that they are as successful as they can be with simulation technology. We're very proud of the fact that around about half of our employees are of a technical nature. So there we are there. That's pretty much all of us. So engineers, specialists covering all of the simulation physics. And it's really part of our job is to guarantee, to ensure that users of simulation software get the absolute maximum they can out of it. And that's why we invest so heavily in our technical personnel. We are based across the UK and the Nordics. So in the UK in Sheffield, we have offices in Norway, Finland, Sweden, and Denmark. And we have technical teams spanning all over this territory. Our main partners, technology partners, are Ansys in the middle, and they're the global supplier of simulation software. And we'll be talking primarily about them today. We also have Rescale for the HPC cloud side of things, and Neural Concept. So a little bit more detail about Rescale then. Obviously, we see a lot of interest in using cloud computing nowadays for simulation. Engineers can often be limited by hardware requirements, needing to do larger and larger simulations in shorter timeframes. So the cloud platform, such as the one provided by Rescale, is a very popular option to perform these calculations. In the middle, then, we have Ansys, the worldwide leader in engineering simulation software. So they provide simulation software covering all physics. And that's really the backbone of what we at EDRMedeso supply. And over to the right, a relative newcomer is Neural Concept. So Neural Concept is a specialized artificial intelligence, or AI, software tool. And this really enhances or complements Ansys simulation by using simulation data to train or teach machine learning algorithms to create a system where you can explore a design space and get results in a matter of seconds rather than waiting for extensive computations. So these are the three technology pillars of EDRMedeso. If we take a quick look into the Ansys simulation portfolio, so these are all the simulation applications that Ansys covers. So as you can see, it's a very wide range of physics. Specifically for space applications, you can really look at this and see that in any product that's designed to operate in space, then pretty much all of this physics is relevant to you. We're actually going to focus quite a lot today on structures, fluids, and electronics, which are really the fundamental areas. And we'll touch on some of the other areas as well with some examples. So I guess the motivation for using simulation software in space specifically is the same as any product, really. There's a phrase that gets used that you've got to get a design right first time, and simulation helps you do that. It helps you test your product in those scenarios that it's going to be operating in. And that's never really more important than it can be in space, where it really has to work first time. So we see a lot of developments on the commercial space side, lots of companies springing up, startups and so on, rapid development cycles, alongside the existing R&D in the academic institutions and the government agencies as well. So a highly active industry area. And again, as I say, very important to get these designs right, and simulation can certainly play a key role in that. So if we consider any product that has to operate in space, you can see that there's all sorts of physics occurring here, and they're not working independently. We quite often have to consider physics interacting, whether it's electronics, cooling, thermal considerations, fuel, propellant management devices, looking at the fluid side there. Then, of course, there's a lot of materials technology that goes into these products as well. So quite a wide array of potential applications where simulation technology can help. So we're going to have a look at a few examples today. And the idea is to give you a high-level overview of what Ansys simulation software can do in the design of products for the space sector. So I'm going to hand over now to my colleague, Rich Davies, and Rich is going to talk about and show you some examples related to structures and structural simulation in space.
Well, thanks, Steve, and good morning, everybody. So I've only got about 15 minutes to talk. So really, what I'm going to give is a light touch introduction to a few examples of structures analysis in the space context, ranging from coupled thermal, optical, and structural analysis, standalone mechanical analysis, impact and explicit methods, right through to PCB reliability and composites assemblies. And then in one example, what I'll do, I'll go into a bit more detail in the steps involved in a CubeSat analysis. So as mentioned, I'm going to focus on the structures subset of the Ansys portfolio. So the subset I've highlighted here, ranging from mechanical, LS-Dyno, and Sherlock right through to design life. But I'm also going to talk about how these products interact with the other physics solvers available. And I think that's a theme that's running through this whole webinar. So first, really, a bit more detail into the various structural products. So on the left here, we've got Ansys Mechanical. Now, this is perhaps the original and the core structural solver of the Ansys portfolio. And it provides an incredibly broad range of implicit static and transient analysis methods, some of which we'll touch on today. So it's capable of structural, thermal, and vibration analysis, amongst many others, and has a really strong focus actually on providing coupled analysis methods with other solvers, which we'll also talk about throughout today's webinar. And then we've got the explicit solvers, so LS-Dyno and Ansys Explicit, which isn't shown here, it's part of the Ansys suite, and then Autodyne. Now these enable analysis of very highly non-linear scenarios, or events which sort of involve extreme degrees of deformation or very significantly changing contact conditions, or which occur over short durations, explosive or hypervelocity events. And then LS-Dyno in particular also offers quite a strong baked-in multi-physics capability with fluid, electromagnetic and thermal solvers baked in. Now we've also got some more manufacturing-oriented products such as Ansys Forming for metal stamping, the additive solution for simulating additive manufacturing processes, and that in fact has been used to great effect in recent space applications. And then we've got Sherlock, which provides predictions for electronics hardware, so looking at thermal durability and vibrational durability of PCB assemblies, for example. And you see here we've got ENCODE Design Life. Now that takes our structural predictions from mechanical and LS-Dyno and other codes, and it provides a fatigue and durability prediction capability. Durability is of particular importance in space where you've really got limited opportunity for in-service maintenance. And then finally, we've got Ansys Motion. Now that's an industry-leading multi-body dynamics solver for analyzing rigid and flexible bodies. And it's complementary to, and it does vastly extend the inbuilt rigid body dynamics capabilities within Ansys Mechanical. So really, you can see there we've got a very full-featured suite for doing structural analysis. Now, clearly in space, the structural response to thermal loading is going to be of key importance, and this functionality is one of the primary analysis methods available in Ansys Mechanical. So we can represent the thermal properties of the various materials, things like the expansion coefficient, or the conduction, convection, and radiance coefficients and capabilities. And we can investigate how those thermal loads will then, and heat transfer will affect the structural performance of our systems. Now, these materials data, they're available within materials databases within the Ansys suite. There is another product called Granta, which is a very full-featured and rich source of materials data. Or you may actually have your own bespoke properties, and ultimately you can input these. So things like your thermal expansion coefficients, or your Young's modulus, or Poisson's ratio of your materials. And what we want to do is we want to predict how these thermal and heat loading will affect the structural performance. So ranging from what you might consider as a straightforward differential expansion problem right through to utilizing things like the latent heat capabilities of wax solidification to provide cooling in heat pipe systems. And I mention that because it was done quite recently on the James Webb Telescope, so I have some level of knowledge of that. Now, in addition, you'll see I've mentioned IcePack here. Now, this touches on the coupling capabilities within the suite, and they're a massive focus within the Ansys environment. And IcePack, that enables a heat transfer solution using a CFD method of sort of circuitry within the satellite components. And this then predicts the conduction, convection, and radiation. And those resulting thermal loads are fed back into mechanical to provide thermal boundary conditions, and that enables the structural response to those thermal loads to be investigated. Thermal fatigue, for example, is of key importance in these structures where durability and reliability are absolutely paramount. So another example, actually, of the importance of inclusion of thermal effects is their effect on optical performance. Now, everything these days needs an acronym, so this is referred to as STOP, so Structural Thermal Optical Performance. And what you can see here, this is an example of an optical mechanism where the transient thermal analysis drives a transient structural analysis. And there's a link to SPIOS in there, which enables optical analysis. So you can see here we've got the transient thermal driving a transient structural, and we've got a SPIOS input there. And this system here, this is subjected to a 3-hour sun load, for example. And so the loading from that exposure to the sun can then interact, or we can generate the thermal loads, we can look at how that affects the deformation of the structure, and ultimately that's going to affect how the optics behave. So you can see that these Ansys multi-physics solutions they enable you to examine these effects in any combination really, and get a really good prediction of what's going on. And it enables us to mitigate and eliminate reliability problems and design safe and effective products. You'll all know it's highly expensive, if not impossible, to replicate the operating conditions experienced in space using physical testing. And so analysis is really therefore essential to underwriting the performance of these assemblies, in this instance structurally, but as you'll see from my colleagues' subsequent presentations, electromagnetically and the fluid responses as well. So what I'd like to do now is run through a small case study on a CubeSat multi-physics solve. So I'm going to focus absolutely on the structure side of things. I'm certainly not going to steal Fatima's thunder, as she's going to talk about HFSS in a lot more detail, but it's worth noting, I think, how closely the analysis methods are coupled. So as you can imagine, when we launch and then deploy these situations, we've got load conditions of highly fluctuating temperature, high and low pressure environments got to be considered. We've got a huge range of vibrational loading. But at all times, we've got to maintain the performance, the structural performance and reliability under all of those load conditions. And one way we can do that, we can set up what we see here. So this is a system of interacting analyses where we feed in our geometric configuration from an HFSS model. We put that into a transient thermal solve. And then the results, so the thermal solve then informs the static structural solve. And then what we can do here, we can get a prediction of the deformations and stresses and strains within the structure. And we can underwrite its performance. Excuse me. But in a similar vein, we know that the HFSS performance is going to be very much governed by the deployed shape of that antenna, that balloon is inflated. And so what we can do a structural solve to get the deformed shape of the antenna. And then this can inform an HFSS solution, which is going to give an idea of the electromagnetic performance of that antenna. So you can see this, it can be a very much a two-way process, and these physics can strongly interact. But I do also want to highlight down at the bottom here that this has been done parametrically. So you can see what we're generating here is also what's called a response surface. And this gives an understanding of the strength of relationship between the structural response and various input variables like temperature change or geometric configuration. And this gives a fantastic understanding of the behavior of this system. And it really informs the engineers and scientists involved of which are the vital characteristics for safely and reliably deploying these satellites. So here we go. This is an idea of the output from the transient thermal analysis. So we've got a heat flux time history. We've got an idea of the emitted radiation. And what we see, ultimately, we get a prediction of the temperature distribution through the structure. And that temperature distribution is then fed into the static structural analysis, and we can predict the resulting deformation and actually the stress and strain distributions within the structure. So importantly, in this case, what we get an idea of the deformation of the antenna. And that deformed shape can then be fed back through to an HFSS simulation of that antenna response. And I'll let Fatima go into the details of this. It's outside my scope and area of expertise or experience. But what you see here is that the nominal shape has a very different response, or a different response to the deformed shape that we're predicting. So to have that deformed shape predicted and informing your HFSS solution is invaluable. But really, I just want to emphasize here, this has all been done within this pretty easy to set up environment. So in Ansys Workbench, where we can use these interacting physics and structural solves to then inform other solutions and vice versa. I've got another example here. This is a composite propellant tank. Again, we've got an acronym, PMD, so Propellant Management Device. And this has to withstand high internal pressures, so in this case, 6,000 psi. But what it is, what I want to highlight here is this is a filament wound product. And so what we need to do is set up this analysis and have a look at how the fibers are distributed within that composite tank. And then ultimately, perhaps we might want to do a dynamic simulation of this, so to look at the modal, the shock, or the harmonics, and random vibration response. And Ansys Composites pre-post was used here to build this model. And what this does, this really does make the generation and the processing of these composite structures very, very straightforward. And I say that from personal experience of having set up a filament winding simulation in the past without tools like this. It's really quite challenging. You know, it's tinged with a little sadness that I didn't have access to this 5 years ago, because it would have saved me an awful lot of time, because it really is a very good tool for setting up very complicated composites analyses. You know, we can look at the structural response when we're deploying and assembling these systems. You know, we need to deploy them. In this case, we've got solar panels reliably, and with the opening sequences very closely controlled. You know, we don't want things like excessive displacement from attitude control events. We've also got to withstand the thermal cycling within the whole life cycle, and we've got to withstand shock and impact loads during launch. So all of these different loading conditions can be built into our analysis systems, in this case, a Ansys mechanical environment. And it gives us an idea then of the sort of an understanding of the system modes of behavior. Thinking about a sort of totally different scale, really, we can also use the same thermal and structural analysis capabilities to look at the physical durability of circuitry, in this case of PCB assembly. And what we're doing here, we're solving this structural random vibration loading in mechanical. And then those data are fed through to a different software package called Sherlock, which is a specific tool for looking at reliability and durability of assemblies like these. And it's another great example of the sort of interaction of the systems where loading and conditions from one specialist solver are fed into another. And so we can get this rich analysis capability within one environment. And then we can even look at the other end of the spectrum, so explicit analysis. And we've got a couple of examples here where Ansys Mechanical and LS-DYNA were used to predict damage resulting from debris impact. I mean, be that the tragic foam debris impact on Columbia, right through to potential space debris impact damage on satellites. And these, as I mentioned earlier, the explicit solves are very much for the highly nonlinear, the sort of very short duration impact events, which is ideal here. It was used forensically in the left-hand case, but it can be used prescriptively in the right-hand case to mitigate the damage that you would get from impact events like this. And then really, no recent space webinar is going to be complete without some mention of the James Webb Telescope. And you'll see in this instance, the engineers, they used Ansys mechanical simulations to look at solutions to the precise mirror pointing as a sort of function of the natural vibrational frequencies of the structure. And mechanical really helped sort of determine the effects of having this connected segmented mirror. So the segments will respond to disturbances, in this case, in the same way that a monolithic mirror would, which is of critical importance. But again, this is coupled with Ansys Zemax in this case to look at the complex optical behavior of the system and the sort of the numerous gold-plated mirror segments they've got. I mean, there's 18 segments in this primary mirror, all designed to function as a single mirror with a surface smoothness of about 100 nanometers. I mean, it's astonishing technology considering the loads involved in even just getting it to a deployed condition. So the engineers used Zemax to sort of design and test every step of that alignment process, really from the initial segment search right to the final phasing. And I do recommend that those two links down at the bottom left there on NASA and Ansys blogs are really worth a read if you have time. They're easily readable and give a fantastic sort of in-depth description of how the James Webb Telescope was designed and how Ansys Mechanical helped out in that. So I do hope I've given a brief and I know it's a very top level idea of the structural response and the structures side of things. So it just stands to me to thank you firstly for listening. And now I'll pass on to my colleague Fatima, who's going to talk about some of the electromagnetics capabilities within Ansys portfolio. Thank you very much.
Thank you very much. Hello and good morning, everyone. Welcome to our webinar. My name is Fatima Howeizavi, and today I'll cover the electronic and thermal physics tools in space application. In next few slides, I'll cover critical areas that are essential in a space application, including communication and data transfer, phased array and beam steering, installed antenna performance, satellite co-site analysis, radar cross-section, ESD analysis, thermal analysis, and simulation system in their operation environments. When we are talking about space, a satellite, the first things is come to mind is the communication, is the data transferring, and the main device can be enable the communication and data transferring is the antenna. As you know, antennas are essential in a space application because they enable communication, data sharing, navigation, and remote sensing. In Ansys HFSS, you're able to create complex 3D model of the antenna geometric. Ansys HFSS use finite element analysis for simulation, which is give you a very accurate data, and also you're able to do analysis such as radiation pattern, gain, impedance, and some other performance metrics using HFSS post-processing. There's optimizer tools in HFSS that help the designer to adjust their antenna parameter for optimal performance. The antenna in satellite, sometimes they can be complex and time consuming to design, especially if you want to choose a type of antenna and meet all the criteria that you need to design, like gain, directivity, bandwidth, polarization, feed type, steering. All of these things can make antenna design so complicated and also time consuming. Another thing is not always people with the antenna background, they want to use HFSS to design the antenna. There might be the situation that people with no expertise in antenna design, they need to have a ready antenna to, for example, integrate it with their system. So there is a tool in Ansys HFSS as the design kit tool for antenna design. This design toolkit, as you can see in the picture, will cover, I think, around 10 or 12 different type of antenna. You just need to choose the type of antenna, material, and some of the requirement that you need, and just with the press of button, it's going to be create a 3D structure of the antenna on the HFSS, and you just can do the analysis and see the result. Another topic which is quite important in a space application is the phased array and beam steerings, which they are commonly used for steering and communication. In HFSS, there is an advanced tool for designing and simulation phased array antenna, and this helps the designer to move from a single unit to array in HFSS. HFSS array feature lets you easily replicate and arrange the original unit, creating a grid or pattern of identical elements. This is very useful when designers they want to design the phased array antenna. And this is really help to speed up and also for scaling up the design efficiency as well. Here, I'm going to talk about how Ansys SBR Plus is going to help the designers and engineers. Just think about when you design a simple or single antenna in the vacuum area or in any kind of area that they are not installed in the electrical large environment. You need to see the performance of the antenna after you install it in the electrical large environment. And this is quite challenging when you are using Ansys HFSS or even any other tools because of normally the antenna, like when they are installed in the satellite structure is basically very large environment, electrical large environment, and it's difficult to simulate. So Ansys HFSS SBR Plus is a high-frequency electromagnetic simulation for modeling EM interaction in electrical large environment. It employs the shooting and bouncing ray, that's why they call it SBR techniques for rapid computation of EM solution. HFSS SBR Plus computes installed antenna performance, extended near field distributions, far field radiation pattern, and radar signatures from electrical large platforms with minimum computation resources. The next topic that I'm going to talk now is about satellite cosine analysis. The satellite cosine analysis is the process used to evaluate and mitigate electromagnetic interference, as they call it, EMI, and electromagnetic compatibility, EMC, issues that can arise when multiple satellite systems or payloads share the same physical platform or operate in close proximity to each other. This analysis is critical in the design and operation of satellite constellation, where multiple satellites work together in a coordinated manner. Satellite cosine analysis in Ansys helps to, first of all, manage system performance data, and then you're able to simulate RFI EMI effects. Then you can identify the root cause of RFI EMI and then resolve the RFI EMI issues. The next important analysis for a space application is the radar cross-section. Radar cross-section is a measure of how detectable an object is by radar. It quantifies the ability of an object, such as an aircraft, ship, or ground vehicle, to scatter or reflect radar signals back to the radar receivers. Radar cross-section is critical parameter in radar system and has important implication for military and civilian applications, including target detection, tracking, and other space technology. And in Ansys, we know that the main challenge in radar cross-section is tests and measurement and design trades-off. With the Ansys tool, we're able to design a radar cross-section for complex structure, and we can do the characterization for different material, and we can do fast and accurate modeling. The next important analysis for a space application is electrostatic discharge, or ESD analysis. In space, there is no atmosphere to protect the spacecraft from radiation. A charge buildup from the radiation can't dissipate because the spacecraft are not grounded to Earth. So spacecraft design must properly mitigate charge accumulation and dissipation on the spacecraft's surface and inside components. When charge accumulates, it includes electric fields. The magnitude of the electric fields may exceed the breakdown of air, plasmas, or dielectric and lead to electrostatic discharge. The damage from discharge can cause total mission failure. There is a design standard are put in place by NASA and ESA to mitigate this spacecraft charging. So for most of them, small company or private sector, meeting this standards and doing the test for meeting this standard is quite expensive and time consuming. But with Ansys EMA 3D charge, meeting this standard is easier and of course less time consuming and less cost. Now, in this slide, I want to introduce Ansys Thermal Desktop. But before I introduce Ansys Thermal Desktop, I just want to highlight and stress about how thermal simulation is important and critical in a space application, because it helps basically spacecraft and their system, they stay safe and functioning in the extreme temperature of space. Without proper thermal management, a spacecraft could overheat or freeze, potentially leading to mission failure or damage to sensitive equipment. By using thermal simulation, engineers can design effective temperature control systems, select appropriate material, and ensure that a spacecraft can withstand the harsh thermal condition of space. So here I'm going to introduce Ansys Thermal Desktop. Ansys Thermal Desktop is PC-based thermal and fluidic analysis tool for heat transfer, thermal radiation, environmental heating, and fluidic flow design. Ansys Thermal Desktop can solve quickly a component to system-level thermal and fluidic problems, enable early design evaluation and rapid design changes, maximize testing efficiency, and the highlight about the thermal desktop is integrated with Ansys Mechanical, Fluent, and STK and Model Central. In thermal analysis, we often don't have precise data before testing, so it's critical to evaluate our design option carefully. The way heat moves through contact and insulation can be unpredictable, and we need to consider the variability in the environment. That's where thermal desktops come in handy. It quickly simulates different scenarios, handles uncertainties, and can adapt to various needs. Here is a thermal desktop workflow. As you can see, the design concept can be modeled using predefined shape and flow networks. Thermal connection, heat loads, radiation, and boundary condition are added, solution generated, and result user customization are available. As the design matures, CAD geometry become available. In a space claim, mesh control and properties are assigned to the geometric. A finite element mesh is generated in thermal desktop and connected to the rest of the model. Here also is a thermal desktop application, and you can see for satellite and thermal loading, for a space launch, for thermal optical design, for fluidic system, renewable energy, and electronic system. These are the applications and industrial that thermal desktop can be used. Another highlight that I mentioned is the integration of the Ansys desktop with the other Ansys tool, especially with the mechanical. And the other hand is mechanical is integrated with the optical HFSS and Sherlock, and this helps the engineers to work better if they are in a different team or if they are not expert in all of the areas. One question probably now comes to lots of you probably is okay, so if there is a for example thermal desktop analysis, so what is the difference between thermal desktop with the other Ansys tools? For the thermal desktop, normally we use it when we have a large system with heat transfer between many components or the environment, like a big satellite or a spacecraft, launch vehicle, and liquid gas storage. When overall thermal control system like surface coating, heater budget, heater exchanger efficiency, a flow in piping network with or without phase change, simulation of long time periods, and also thermal radiation is a major design consideration. But when we use other Ansys tools like IcePack, Mechanical, Fluent, mainly we use them when we are designing and analyzing the details model, detailed circuit boards, component, heat exchanger, or undefined fluid flow. In last two slides, quickly I want to talk about STK Pro. And the STK Pro is the modeling and simulation complex system in their operational environment. With system toolkit SDK, you model complex system inside the realistic and time dynamic three-dimensional system that includes high resolution train imagery, RF environment, and more. And the other things about the SDK is the SDK has the integration with the thermal desktop. So it's use the data from the SDK can come to the thermal desktop for the thermal analysis, which is something is very helpful for the space application. And the last tool I'm talking about is the ODTK tool, which is industry solution for orbit determination software with call it ODTK. You can process a wide variety of traditional and non-traditional measurement to generate orbit with realistic covariance. ODTK can combine diverse set of measurement type into one seamless result, enabling you to track objects from ground, space, sea, and air using any other technology. So, thank you for your time.
Okay, so it's Stephen back with you, and we're going to round out the webinar by just showing a couple of examples of how Ansys simulation can be used with the purpose of solving fluids type applications in space. So first of all, we're just to refer back to the product portfolio here. This is the fluids product set here. So you can see when we say Ansys CFD, we actually refer to a number of specialist products. So over on the left, we've got the Fluent and CFX CFD solvers. So these are general purpose solvers, which you can apply to a multitude of different types of analysis. Then in the middle here, we have some specialist solvers. So things like ChemKim Pro, that's specifically designed for chemical reactions, combustion, fuels, and so forth. Moving along, we have materials processing. So that's really manufacture in the form of polyflow, icing, aerospace icing, FENSAP ice, particulate simulation, and over here we have thermal desktop, which is coupling different solver physics for thermal applications. We're going to focus primarily on the general purpose CFD side, though. One of the most interesting applications that's relevant to space is it's actually fuel sloshing, and there's a number of things that CFD can do to assist in the design process here. So it may be looking at flow through valves, it may be looking at evaporation, condensation in tanks, filling, sloshing, emptying, and also fluid structure interaction. So this is where we can use the CFD solver to very accurately simulate the movement of a fuel in a tank. And then we can use those pressures and forces to map across to a structural solver, which can then look at the stress and material implications of the movement of that fuel. So we'll look at propellant management device tanks and a couple of simple applications. So why would we need to do this? Well, if we have fuel sloshing, even on a ground-based application, if you think about your car when you're braking, or a tanker truck, it's got a large mass of fluid inside it. Movements of that fuel can create huge forces. So it's very, very important that that's considered during the design process, because that has massive implications on stability and so forth, and can cause all kinds of problems there. It's traditionally been accomplished by, there's various analytical methods. So, for example, sloshing motion during flight conditions, there's methods such as pendulum or spring mass systems, which can go so far, but they have their limitations. Really, the only way to get as close as possible to the movement of a fuel inside a tank is to use a CFD analysis. So CFD using Ansys Fluent, that can provide that insight. All we need to do is to provide the representative operating conditions. Once you've done that, then you can get the entire operating cycle of a propellant tank, all of the forces, pressures, and so forth. And that's just going to lead to a better tank design. So generally, rockets powered by liquid fuel, which is generally stored in a pressurized tank. That then is subject to gravity forces and inertial forces as the rocket is under motion. So normally we'd have pressurization with an inert gas inside the tank, and as the fuel is getting depleted, then that's accompanied by movement of the fuel or sloshing, which causes forces onto the tanks. There's also the possibility of getting aeration. Some of the gas can get entrained into the liquid in the form of bubbles, which can then get into the engine ducts and into the engine. So things that we want to avoid. Primarily then, we do this to promote stability. We want to promote continuous uninterrupted delivery of fuel to the engine and eliminate the possibility of any kind of engine malfunction due to gas bubbles getting entrained into the engine itself. So this is a simple case study here, which we've been completed using Ansys Fluent. So we've got a capsule tank over here, and you can see we've got the computational mesh there, and this is the fill level. So 50% filled with liquid. And this tank is actually a drop test. The data that we used is available from NASA there, and the simulation runs the experience of the tank according to the motion profile, and we can see how that fluid moves in accordance with the forces acting on it. So these are typical motion profiles that we'd use as an input into Ansys CFD. So we've got the Z and the X profiles here, which give us the acceleration that the tank is subject to. So this ramps up for just 0.08 seconds. The simulation time is just over 1.5 seconds. Now, when we run the simulation, this is what we get from Ansys Fluent. So the coloration here, this is actually a scale from 0 to 1, which represents a volume fraction of the fluid. So where it's red here, that's meaning that it's 100% fuel. The blue is the gas. Now, what it can do, what it can output at each time step is the precise position of the fuel as the tank is subjected to those external loads. So you can see that compared to any analytical method, the CFD is able to give us a very, very accurate understanding of what's actually happening to the fuel as the tank is subject to the loads that it would be under operation. So you can see the interface between the fuel and the air is very accurately captured. Now, having this information then gives you a much better chance of designing mitigation methods that can either control the motion of the fuel, or at least give you an understanding of how that motion is going to create potentially other problems, such as the forces as it's impacting the side of the tank and any possible air entrainment. So typically then these are the results that we get out of this CFD simulation. So I've got the force over time of the 1.6 seconds that this was run. Another example using a similar tank here. So again, it's capsule tank. This simulation using CFD replicates the launch conditions of the tank. So again, we've got a tank which is initially full or filled with liquid fuel, pressurized, and we've got helium flowing into the tank from the inlet. As the launch process goes through, that fuel is obviously depleted, and also the tank is subject to external accelerations. So typically then, this is the input profile that we have here. So acceleration in terms of horizontal acceleration and vertical. So the horizontal acceleration there is giving us the sloshing. And this simulation is run for the first 250 seconds of the mission. And this is just a typical representation of the tank trajectory as it's being launched. So I've got an animation here, which I'm going to show you. This has been completed by Ansys. So you can see that the CFD is able to give us both the depletion of the fuel and the motion of the fuel as the vehicle goes through its launch process. So we can see here the fuel mass is decreasing. And as the vehicle changes its orientation, you can see the impact of the accelerations on the fuel itself. Okay, and hopefully from this animation, you can see that level of detail is far beyond anything that you could get from more of a simple analytical method. So using CFD in this way gives you data that is as close as possible to the real experience of the fuel sloshing during a launch procedure. Okay, so that was the first example I wanted to show you. So we've shown how CFD can give you information that helps you understand the stability, helps you understand any potential entrainment of air bubbles and so forth. And with that information, then you can design either the product itself or make adjustments to the mission to mitigate any of those issues. Another example that I'd like to look at here is this is more of an aerospace example. So we're looking at the actual launch, separation, deployment, and impact and recovery. So this is where this is quite a traditional application of CFD in the aerospace world. So we're looking at atmospheric impacts here. CFD lends itself very well to external aerodynamics. So essentially simulating the airflow over an object, and at high speeds, we have to think about things like viscous heating and so forth. Another factor to this is that we can use CFD in conjunction with another physics solver. So, for example, mechanical. And here we have a nice application of fluid structure interaction on an external bluff body. So what we're doing here is we're running the CFD simulation to give us the pressure and force data, and then we're passing that over to a structural simulation using Ansys mechanical. And this can happen. It can be a one-way transfer. So, for example, where aeroelasticity is quite minimal, or where you have large deformations, you can do a two-way analysis where data is passed back and forth between the two solvers. So, as you can see here, where we have large deformations, then this would be a 2D, a two-way FSI analysis. The operating environment in Ansys makes this really, really easy. You can just drag and drop different analyses onto each other, and they will just pass the data between them. So just in general then, multi-physics, that's an example of fluid structure interaction, but you can also combine electronics. You can exchange data between any one of these three solvers. And that's increasingly important because not just in space applications, but anywhere, you have to consider the coupling between physics. So back to our little case study then, the sounding rocket through the atmosphere here. We've got our input profiles here, so Mach number, altitude, angle of attack, temperature, pressure. We're conducting a CFD analysis to get the external aerodynamics forces that are occurring here, and we're combining that with a structural analysis to look at the thermal effects of the materials in the actual craft. So typical results then from this type of analysis here, first of all, looking at the external airflow here. So we've got our Mach number contours. at different times from 0 to 30 seconds. We've got our external fluid temperature contours here, again from 0 to 30 seconds at different parts of the operating cycle. And then we can start to look at the thermal structural side. So start to look at wall temperatures and internal component temperatures. Okay, so that's on this slide. This is the Ansys mechanical analysis. So this is conducting a thermal analysis of the internal components based upon data that it's received from the CFD analysis. So a nice simple example of how you can use CFD and combine that with structural thermal mechanics. So we use this to simulate a transient re-entry and look at aerothermal behavior. Essentially we're using what we call system coupling or multi-physics, and that's used a number of data transfers. So we're transferring near wall temperature from the Fluent CFD solver to mechanical, a heat transfer coefficient from the Ansys CFD Fluent solver again to mechanical, and then we're taking wall temperature back from mechanical to Fluent. But that's just one example of multi-physics. Again, you can include structural deformation. You can also include electronics solvers as well. Okay, the options for that kind of analysis are either steady, so where you have a steady frame of reference, or fully transient. So if you think back to that deforming bluff body that I showed you, that would be a fully transient two-way FSI. Depending on the precise circumstances, you might be able to simplify that and have a one-way FSI. The difference is essentially compute time, but either one of these methods is available and made easy for you to do. Okay, so I'd like to conclude the fluid parts of the presentation here, and I'd like to hand back to our host. But just before I do that, I'd just like to thank you for your attention. And hopefully you've seen some examples here which have are interesting. And if you do require any further information on anything that you've seen today, we would be more than happy to open a discussion with you. So thank you. I'll hand you back to your host for today.
Thanks, Stephen. Well, I'm sure you'll all agree there was a lot to take in here. If at any point you would like to see any part of today's presentation again, you will all receive a link to this webinar's recording, which will be posted up to our website in the next few days. Thanks to everyone who has asked questions. We very much look forward to following these up in plenty of detail. Thank you to our speakers, Rich Davies, Fatima Hovezavi, and Stephen Sylvester, and thanks to all of you for tuning in. We very much hope to see you at a future EDRMedeso webinar. Goodbye.